Good afternoon. Wei Cao is not able to join us due to a family emergency, but he wanted to extend his greetings. And he, as the founder and CEO of Lumen Labs, he is 100% dedicated to the mission of bringing a new technology to help keep people safe. He's really passionate about Far-UV, and along with the unfortunate circumstances that made it so he couldn't come. It's really tragic that he couldn't come here. He's been pouring his heart and soul into Far-UV for the last 4 years. So just wanted to give a quick introduction about who Lumen Labs is. So we're an OEM, and our background is in manufacturing. And Lumen Labs is 100% dedicated to Far-UV, and that's what we're trying to develop, the best Far-UV available on the market. As I said, our background is in manufacturing. The parent company, if you will, is FES International, a contract manufacturer and a joint development manufacturer. We've been in the business for over 20 years, and we work with Dell, Logitech, and other tier 1 ODMs. But we've specialized in the last 16 years in really high performance lighting for the broadcast industry, and really that led us into being able to design and develop Far-UV solutions. We develop all our bulbs, filters, power supplies, and we've partnered with some other folks in sub-branding and bringing our technology into the market. Our R&D resources are in the US and in China, and we have manufacturing centers in Shanghai and in Thailand, just outside of the capital. Contact information up there. You need to get a hold of us. Please visit us down at the table downstairs, and love to talk with you. We've done a lot of research with other partners, and we're open to participate and further the science if you need partnerships and fixtures. So we have participated in other studies with third parties, with other education groups, but we wanted to see for ourselves how our fixtures were working. So really what we did with this experiment was, can we discern a difference in outcome in a working environment at Lumen Labs with different dispersion of our products. So taking the baseline that Far-UV is efficacious, and we've seen plenty of the presentations throughout the last 2 days on these studies, and then we really wanted to constrain it to being safe. So the TLV limits, we want to make the most efficacious application of Far-UVC, but then again, we need to keep it safe. So that's something that we've all wrestled with. Our original lights weren't completely evenly dispersed in the output, and in which case you have to throttle back the output, or the output actually has hotspots if you measure at different angles of incidence from the bulb. And then if you throttle it back too much, you're not doing the job of disinfection. Another challenge with deploying these in real world environment is the ceilings are really low. So you can get into chambers, you can get into testing, and hypothetically at the right ceiling height, you can have this great coverage in a room, but a lot of ceilings in schools and other environments make that problematic. And then the airflow is an issue. So anyway, we wanted to basically not wait on some longer term testing that we're conducting with other partners, and we wanted to do this test in-house. And the problem statement is how do we design a Far-UV solution to maximize the efficacy while maintaining safe and TLV compliant solution. And this illustration is really simple, and that's essentially what the research is going to try to cover. And that is, if you look at our Luminizer 300 fixture, it has tiltable bulbs, and you can aim the bulb straight down, which will create a higher radiation in the center, and you can tilt the bulbs out to a 45-degree angle. This is the first piece of future research where we're going to do some different testing with different bulbs. So the beauty of this study in its simplicity is we're using the same fixture, we're using the same output, we're just tilting the bulbs slightly further out, and we want to see, you know, what does that do to the efficacy and what is that doing to the safety input. The illustration of the Luminizer 300. All our bulbs are filtered, and the distribution of one of three lights in the Luminizer 300 is a 60-degree beam angle. So the methods used and the tools used in this research for sampling, we use a 6-stage sampler. For culturing, we as you see there, we use the culturing incubator, and we place petri dishes around the room, and then we were also monitoring for ozone. This is a simple illustration of the room. On the left is the 0 degree. On the right is the 45 degree. So again, this was an active office in Shanghai at our headquarters. The room size was 5 meters by 4 meters by 3 meters. And one luminizer was mounted in the middle of the room on the ceiling. Windows were kept closed. There's a single wall air conditioner, which was recycling air, so we weren't introducing any outside air into the room. And 4 employees were used for the duration of the study. So the same 4 people, 8-hour periods. TLV measurements were taken both at the at the 2.1 meter plane and then the 1.8 meter plane. And then the 2 sampling units were set on the table. The room occupants were sitting, working it for that 8-hour period on either side of the table. And then we had the ozone monitor sitting at the edge of the table there. We use a tool, Dialux, to simulate what the output would be of our fixtures, but this kind of gives you an illustration of the 0 degree angle. You can see in the orange and red significantly more energy hitting the center of the table, and then at 45 degrees you can see more dispersion throughout the room. Okay, there's a picture of our enthusiastic participants, and there was a 5th person involved who would come in a clean suit and come in and take the petri dishes and place them and remove them. But for the most part, this was their work environment for the entire day, except for getting out, leaving for lunch, coming back, or having to take a bio break. So 5 days of testing with 8 samples collected every day. One day was a control day with no Far-UV and no people in the room. Another control day with no Far-UVC and people in the room. Then there was a test day with the 0 degree beam angle, a test day with the another control day, and then a test day with the 45 degree beam angle. So pretty simple process and protocol. And so this again is the beginning of more longitudinal studies that we hope to do, but essentially we have one day where we're doing the 0 degree beam and a second day with the broader beam. So here's the data. And you can see in red are the control days. So, sorry, let me repeat that. So down here in the gray line, that's the control day with no people and no Far-UVC. Then we introduced in the red line, we had the 4 people in the room, and this was the data that came out with the colony forming units. So we can see the numbers for no people, 4 people introduced to the room, and then the green line we have the data that came out with 0-degree beam angle, then a control, and then the dispersed beam. So we're seeing significant reduction in both scenarios between a 0-degree and a 45-degree. And again, this was the data coming from the ozone collection. So I think this just proves what we all know is introducing Far-UV into the space significantly reduced the pathogens in the air or the material in the air that was collected. But the data you can see is pretty, there's a variation between the 0-degree and the 45-degree. So on the left here, we have the CFUs collected on an hourly average between the 0-degree and the 45-degree. And we could summarize it with a percentage, both impressive reductions, slightly higher with the 45 dispersed beam, and then with the peak reduction rate, we see an 83% and a 92% reduction. So that proved the efficacy side of our test. And we wanted also to make sure that we're adhering to safety. So for the 0-degree beam, the chart over here is actually showing 8-hour at the 1.8 meter height. And then we have the old TLVs versus the new TLVs. And so we measured for the 0-degree at 178, and then at the 45-degree at 46. And so we were exceeding the TLV limits. For 18, this statistics is a bit confusing, but for 18% of the room, if you were in that position, we tried to illustrate it with the red dot. For 18% of the room area, you would be exceeding the TLV values. And then with the 45-degree, you were not exceeding the values at all. So that's a different way to say it, is that in the previous slide, we were achieving higher reduction and maintaining safety on this illustration here. And that's true both at both heights, or at both heights and at both the old and the new TLV limits. It's a different way to look at the data, and that the conclusion is that by modifying the output of the filtered Far-UVC bulbs through distribution, we can improve the efficacy, and we can maintain or improve the photobiological safety. So on the blue, we see the hourly average disinfection with the tighter beam, and with the orange, we can see the broader beam. And then comparisons with the photobiological safety, you can see 0, we did not we did not go over TLV at all with the dispersed beam. And there were areas in the room that we exceeded TLV. So that was our first step at taking the fixtures that we have had on the market for the last several years and proving what our hypothesis was. And that was more dispersion. Not only do you get a efficacy improvement, but you'll also get a safety improvement. So for the future, there's certain things we'll go try to achieve, and that this particular research doesn't address. And this is a very small sample set, so we like to continue this in a larger time duration, a variable room setup, but also this doesn't, as far as real world applications, this doesn't take into account some of the other issues that were brought up in the previous talks, and that is, what about airflow? So we intentionally closed the windows in this room, and there was no external air coming in and out. We'd like to take samples at different times of day. But also, a real world environment would be lots of different people coming in and out. So this is almost real world, but it was controlled. And then we don't know if the CFU reduction truly translates one-to-one for infectious pathogens. So we've designed and developed a new lens, and this lens has even more distribution than the lens that was used in this study. And what we've achieved with this new lens is a 1.5 increase in output, but we've broadened the beam angle. So with the same idea that there's more distributed energy, and we should not exceed the TLV with this distribution. And this is different than adding, say, a filter, which would also achieve distribution, but would significantly subtract the energy that you're putting into the room. So with this new lens and filter design, we hope to prove the same kind of efficacy and safety that we did in this test. I think that's it. Take some questions.
One question down here in the front.
Chris Bowers with Exemer. I was wondering, I have a question and a possible follow-up question. Do you have CAD files and IES files and things like that for your lamps? And if you do, are those available, or would you be willing to make those available so that we could possibly test with simulations using some of your lamps without before purchase?
The answer is yes to both questions. We have IS files, they're available, and I'll leave it at yes.
Great, thank you very much.
Thank you.